The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Last time we saw that these electron configurations that you've been writing down are nothing other than a shorthand way of writing down the wave functions for each electron in a multi-electron atom within the one electron wave approximation, where we let every electron in the system or in the atom have its own wave function. And as an approximation, we gave it a hydrogen atom wave function. But we also saw that we did not, that at most we gave two electrons a hydrogen atom wave function, the same hydrogen atom wave function. And of course, you already know that the reason we did that is because of this quantum mechanical concept called spin, quantum mechanical phenomenon called spin. Spin is the intrinsic angular momentum. It is the angular momentum built in to the particle. And that angular momentum comes in sort of two polarities, a spin up and a spin down, corresponding to the two possible values of the spin quantum number m sub s that we looked at last time. M sub s can have the value plus 1/2 or can have the value minus 1/2. All right. So we're about to talk about how spin was actually discovered. And was discovered by these two gentlemen here, George Uhlenbeck and Sam Hutschmidt. And they were really very young scientists. They might have been postdocs at the time. And what they were looking at was the emission spectra from sodium atoms. And this is 1925. And so they already knew enough about the electronic structure to anticipate where the emission, to anticipate at what frequency they ought to see emission from the sodium atoms. And so they got a discharge going, looked at the emission, dispersed it, and, well, they thought that they would see some emission at this particular frequency, but instead what they saw was some emission a little bit lower in frequency where they expected and a little bit higher in energy than what they expected. In spectroscopy, this kind of emission here is called a doublet. Okay, a little lower and a little higher. Well, they looked at these results, thought about it, and said, you know, I think we can understand that, those two lines, those emissions at the two frequencies there, if the electron, in particular that extra s electron in the sodium, if that existed in one of two spin states. So this was a revolutionary idea. And so they were quite excited about it, and they took the results of their experiment and their interpretation to the resident established scientist at the time that was closest to them, this guy, Wolfgang Pauli. Wolfgang Pauli was not a nice man. So they showed him the data, and they said, oh, yeah, this makes sense if the electron's in two different spin states. And Wolfgang Pauli said, rubbish. You publish that, and you'll wreck your young scientific careers. So Uhlenbeck and Hutschmidt left dejectedly. No sooner than the door slams shut, and Pauli sits down and he writes a paper on the presence of the fourth quantum number, m sub s. This is one of the best well-known travesties in the history of science, now well-known. Okay? And it actually took, however, another 3 years, and it took another gentleman, Dirac, It was Dirac who actually wrote down the relativistic Schrodinger equation and solved it. And when you do that, out drops this fourth quantum number, m sub s. Okay? However, Pauli did contribute to this problem in the sense that he worked on the principles behind these problems with electrons being fermions, et cetera, which we won't go into. But out of that work came something called this, the Pauli exclusion principle. All right? And the essence of that principle is that no two electrons in the same atom can have the same electron wave function or the same spin. Or another way to say that, no two electrons can have the same set of 4 quantum numbers. Okay? So for example, in our electron configuration here of neon, this electron has the quantum numbers 100 plus 1/2 for m sub s. This electron has the quantum numbers 100 minus 1/2 for m sub s. So these two electrons don't have the same set of 4 quantum numbers, right? And that's why we could only put 2 electrons here in this 1s state. Okay. Likewise, this electron here has the quantum numbers 2, 1, minus 1, plus 1/2. This electron has the quantum numbers 2, 1, minus 1, minus 1/2. Okay? So that's the Pauli exclusion principle, which prevents us from putting more than 2 electrons in each one of these states, 2s, 2s, 2px, 2pz, or 2py. Okay? Okay. So now what I want to do is I want to try to look at the wave functions. I want to look at what these wave functions look like for the electrons in the multi-electron atom. And to look at their shapes, what we're going to do is we're going to look at the radial probability distribution function. Because remember what the radial probability distribution function tells us. It tells us the probability of finding the electron between r and r plus dr. Okay? So I plotted those radial probability distribution functions versus r for each one of the electrons in the different states for this multi-electron atom, argon. Okay? And what we want to do is we want to compare and contrast these wave functions for the individual electrons in this multi-electron atom to those of hydrogen. All right? All right. Well, first, the similarities. If you look at this wave function, or if you look at the radial probability distribution for the 1s wave function here, what you see is that that radial probability distribution is 0 at r equals 0, as all radial probability distributions are. That's not a radial node. That probability distribution increases, goes to a maximum, and then decays exponentially with r. Hey, that's exactly what a 1s wave function looks like for a hydrogen atom. If you looked at the 2s wave function, it starts at r equals 0, goes up a bit, and then goes to 0. Here's a radial node in the 2s wave function. And then goes back up. Here's the most probable value of r, then decays exponentially. Hey, again, it has the same structure as the 2s wave function in the hydrogen atom. So the similarity is that all of these wave functions have the same kind of basic structure as that in a hydrogen atom. They have the same number of nodes, same number of radial nodes, same number of angular nodes. All right? The difference between these wave functions and those of the hydrogen atom is that all of these wave functions are closer in to the nucleus. So for example, if you looked here at what the most probable value of r is for that 1s electron, that most probable value in argon is 0.1 A0. What's the most probable value for r in the 1s state of hydrogen? A0. This is 10 times closer, all right? This is much closer to the nucleus than it is in the hydrogen atom. And if we went and we compared the most probable values for 2s, 2p to those of hydrogen and 3s, 3p for those of hydrogen, we'd find that all of these are much closer in to the nucleus. Why? Because the nucleus has a larger positive charge on it, right? The Coulomb interaction here is the charge on the electron times the charge on the nucleus. For argon, that charge is plus 18 times E. That greater attractive interaction pulls those electrons in closer to the nucleus. That's the bottom line. Okay? So that's how these differ. The structure's the same, no structure's the same. They're just all closer into the nucleus because of that greater attractive interaction. Okay. So now that I have this radial probability distribution function up here, I also want to use it to just illustrate a concept that I think you already know, and that is this concept of a shell. You know about the n equal 1 shell, n equal 2 shell, n equal 3 shell. And the word shell also denotes some kind of spatial information, right? And I want to show you how the spatial information is depicted here on this graph. I want you to see that for the n equal 3 states, 3s and 3p, well, the most probable value isn't exactly in the same place, but it's in the same place as when you compare it to the 2s and the 2p, right? You can see how well the n equal 3 shell is separated in space from the n equal 2 shell. Again, the most probable value for 2s and 2p aren't exactly in the same place, right? We saw the 2p is actually a little closer than to 2s, but in terms of comparing it to where the most probable values are for 3s and 3p, hey, that's much closer in, all right? And so this graph here, it shows you, it gives you an idea of the spatial information that is denoted when we talk about shells. The n equal 3 shell is further out, the n equal 2 shell is closer in, and the n equal 1 shell even closer in. All right? I think that's a concept that you mostly know, but here you see it on the radial probability distribution. Okay. So now we've taken a quick look at those wave functions. Now it's time to actually look at the energies of the states. We haven't done that yet. So on the left here, I show an energy level diagram for the hydrogen atom. Right? We saw this before. Here's the n equal 1 state. Here at n equal 2, we've got 4 states, 4 degenerate states. Here at n equal 3, we got 9 degenerate states. Here at n equal 4, we got 16 degenerate states. Okay, but the difference between the hydrogen atom and any other multi-electron atom, starting with helium, 2 differences. One is that the energies of these states in the multi-electron atom are all lower than they are in the hydrogen atom. That is, the 1s state here is lower in energy than the 1s state in the hydrogen. The 2s is lower than the 2s state in hydrogen. The 3s is lower. The 2p is lower. The 3p is lower, et cetera, et cetera. The energies of those states are all lower. Why? Because of the charge on the nucleus. That potential energy of interaction is greater because the charge on the nucleus is larger. That greater potential energy of interaction lowers the energy of the states, makes those electrons more strongly bound. So starting with helium, all of these energies are lower than those in the hydrogen atom. Okay? That's the first difference. The second difference is you can see now that the 2s state is lower in energy than the 2p state. the degeneracy between 2s and 2p in a hydrogen atom is lifted, or is broken, as we say. Likewise, the 3s state is lower in energy than the 3p state, than the 3d state. The degeneracy in those states is lifted, or it's broken, right? So that's now what we have to talk about, is why that is the case. Why is 2s, for example, lower in energy than 2p? And the reason for this has to do with the phenomenon called shielding. So we have to talk about this phenomenon, shielding, and we have to talk about how that leads to a concept called effective charge. Okay, but to do that, I'm going to do the following. I'm going to realize that each one of these energies here, E sub NL, right? So now these energies are labeled by both the principal quantum number and the angular momentum quantum number. I'm going to realize that these energies here physically are minus the ionization energy, right? Because these energies are minus the energy it's going to require to rip the electron off from that particular state. And I'm going to set those binding energies equal to a hydrogen atom-like energy level here. And now I'm going to use the board, and we're going to explain that just a little bit more. Oops. Okay. So I said these energies, which are now a function of N and L, they're minus the ionization energy from that NL state. And I'm going to approximate that as a hydrogen atom kind of an energy scheme. That is, I'm going to set this equal to R sub h, the Rydberg constant, over n squared. But out here, there's going to be a z. But this z is going to be z effective, Z-E-F-F. And it's going to be squared, of course. And that z is going to depend on the particular NL state that you're in. Okay? This z effective here is the effective nuclear charge. It is not the nuclear charge. It's the effective nuclear charge. Why? Well, because of shielding. So let's try to explain that. So let's take helium. All right? Helium, Z is equal to plus 2E. All right? So we have plus 2E here. And now let's do a thought experiment. In that, we're going to take electron number 2 here, right? And we're going to place electron number 2 kind of close to this plus 2 charged nucleus. And then we're going to have electron number 1 way out here, right? So in this case, with electron number 1 way out here, well, the nuclear charge that electron number 1 experiences, because it's so far out, that nuclear charge kind of looks like a plus 1 charge, right? Because this electron, on the average, is canceling one of the positive charges on the nucleus. So the effective charge here for this electron way out there, we're going to say, is plus 1. If that's the case, well then the binding energy of that electron, right, is 1 squared times R sub h over n squared. All right? We're going to consider n equal 1 because we're going to talk about the ground state of the helium atom here. But you know what this value is going to turn out to be. It's going to turn out to be minus 2.180 times 10 to the minus 18 joules. Hey, that's the binding energy of an electron in a hydrogen atom. Okay? Wait a minute. This is a thought experiment now, right? So this is helium. This is just one electron way out here. And it can't discriminate too well between the nucleus and this electron, so the overall effective charge it sees is +1. All right, but now we take the other case. The other extreme case is we're going to bring in electron 1 really close to the nucleus, right? And electron 2 is way out here, such that electron 2 doesn't do anything as far as this electron is concerned, right? And so this electron in this case is experiencing the total nuclear charge on the nucleus. And so we say in this thought case here, with this electron really close, that the effective charge is equal to +2e for this electron. Well, if that's the case, we can calculate the binding energy of this electron, and that's going to be 2 squared over times r sub h over 1 squared. We can plug in r sub h, and we're going to get minus 8.72 times 10 to the minus 18 joules. Okay? What this is the binding energy of a electron in helium plus, right? Okay. And so in this extreme case with the electron really close in, that's the binding energy. With this extreme case with the electron way far out, this is the binding energy. This is total shielding. This case is no shielding. No shielding. The electron is much more strongly bound. The reality is that the binding energy of an electron in helium is somewhere in between, right? That is the ionization energy for helium. For an electron in now neutral helium here, the ionization energy is 3.94 times 10 to the minus 18 joules. Somewhere in between this extreme case of total shielding and this extreme case of no shielding at all. And that's because on the average, right, there is another electron in between that electron and the nucleus. And we can calculate the effective charge then from the experimental binding energies by just taking this expression and rearranging it, right? So I'm going to solve that expression for the effective charge, Z, E, F, F. And when I do that, that of course is n squared times then the ionization energy over the Rydberg constant, right? N squared is going to be 1 because we're talking about the ground state. The ionization energy, I said, was 3.94 times 10 to the minus 18 joules. Rydberg constant is 2.180 times 10 to the minus 18 joules, right? In the end, I find an effective charge here of plus 1.34. Okay? And again, why is that the case? Well, that's the case because if here's my electron, here's my helium nucleus, well, just on the average, right, between this electron and the nucleus, there's always another electron around. This electron kind of partially shields this nuclear charge. Partially shields it so that we calculated, from using this scheme and using the experimental ionization energies, we calculated an effective charge of 1.34. Okay? All right, so now we sort of understand shielding and effective charge, right? That's a square root. Thank you. Right. Okay. All right. Okay. But now we have to use this idea of effective charge and shielding to understand why the 2s state is lower in energy than the 2p state. All right, and here comes that. All right, let's think about the lithium atom. All right. The electron configuration of lithium is 1s2, 2s1. The electron configuration of lithium is not 1s2, 2p1. Why? Because 2s is lower in energy than 2p. But why is that the case? Well, to look at that, we got to look at the radial probability distribution functions for 2s and 2p. So here's the radial probability distribution function for 2s. Here's the radial probability distribution function for 2p. Okay. Now, you have to do a thought experiment here. In this 2s radial probability distribution function, what you see is that there is some finite probability of the electron in the 2s state being really close to the nucleus. For the sake of the argument here, I'm going to say that for this part of the probability distribution function, for that part, the effective charge, Z effective, is going to be plus 3e. Okay? I mean, that's an exaggeration because obviously we have some s electrons, but for the sake of this argument, I'm going to say the effective charge for this part of the probability distribution function is plus 3e. For this part of the probability distribution function for 2s, hey, that's much further out, and I have those 1s electrons closer in, so for the sake of this argument, I'm going to say that these s electrons completely shield the nuclear charge. And so the effective charge for this part of the distribution is plus 1e. Okay, now what about 2p? Well, in the case of 2p, you can see that this 2p wave function, although it's a little bit closer in, hey, for the most part, it is about in the same place as this, the second lobe here of the 2s wave function. So we're going to say that this effective charge is plus 1e, just like this lobe of the 2s wave function. But now to get the kind of total effective charge, I'm going to have to take the effective charge and average it over this probability distribution function. And so, since in the 2s function, I'm going to average over a part that has a plus 3 effective charge and a part that has a plus 1 effective charge, well, if I average over that, that's going to be larger than the effective charge of this 2p wave function, right? Because the 2p everywhere is plus 1. So the effective charge here for the 2s is going to be greater on the average than for the 2p because of this part of the probability distribution function, this part that's really close to the nucleus, where the electrons can feel more of the nuclear charge or experience more of the nuclear charge than they could if they were a 2p electron. Okay? So therefore, since that 2s electron has a greater effective charge here, well, what that's going to mean is that the binding energy of the 2s state is going to be lower in energy. It's going to be more negative than the binding energy of the 2p state. Same thing for 3s and 3p. All right? Same reasoning there. And it's all because of this little part of the probability distribution function. All right? So now we can understand why the 2s is in fact lower in energy than the 2p. All right? Yeah. The 3, well, because the 3s, although it does in fact have this, it's a little bit further out here, enough to make for this to compensate. But again, 3s is lower than 3p, right? So we're just going to compare 3s and 3p within the same shell, all right? Okay? Yes, right. It does have to do with the net area underneath. If the probability were much higher, and it's not that much higher, but if it were, then you're right. It could cancel it out, right? Right. Okay? Okay. So now, therefore, we're ready to write the electron configurations of all the atoms on the periodic table. And you already know that we use the Aufbau principle to do that. Aufbau means building up. So what do? You take all the states, the allowed states, and you order them according to their energy. Most strongly bound or most negative energy goes on the bottom, and next most negative energy, on and on. And we'll talk about a mnemonic for remembering those energies in a moment. Okay? All right, so we use the Aufbau principle. We start with the lowest energy state, and we put an electron in. For hydrogen, there it is, 1s state. For helium, well, we also put that into the 1s state, except as we fill these states, we have to heed the Pauli exclusion principle. So this electron here goes in with the opposite spin. All right, next, lithium, 2s electron. For beryllium, another 2s electron, opposite spin. And then for nitrogen, electron here has to go into the 2p state. Now, it doesn't matter whether you put it in 2px, 2py, or 2pz, they're all the same energy. Okay? All right, but now the next electron, carbon. What are we going to do here? Well, here we have to obey something called Hund's rule. And Hund's rule says that when electrons are added to states of the same energy, and that's what we're doing here in the 2p, a single electron enters each state before a second electron enters any state. And those single electrons have to go in so that the resulting spins are parallel. That is, they have the same spin. So, do we put in an electron like this? No. Do we put it in like that? No. Do we put it in like this? Yeah. Okay, according to Hund's rule. And then the next electron has to go into that other empty p state before any of these states double up. All right? So then we keep doubling them up. Next electron has to go into the next state, 3s. Again, we double them up. And now we're to the 3p state again. One electron goes into 2px. The next electron will go into either 2py or 2pz, according to Hund's rule, and the spins remain parallel to get the lowest energy configuration. And then the next electron, 2pz, and then we start doubling up. All right? And we keep going. And you keep going in that way so that you write the electron configuration of all the atoms in the periodic table. Okay, let's look at these electron configurations kind of quickly here. Let's start with the third period, the third row here. Sodium going across here to argon. Here's the electron configuration for sodium. notice here that I don't mind if you write that electron configuration as 2p6 instead of 2px, 2py, 2pz, because you can't tell the difference between x, y, and z anyway if you're not in a magnetic field. Okay? These electrons here in sodium that make up the inert gas configuration argon, of course, are the core electrons. So when we talk about core electrons, we're talking about the electrons that make up the nearest rare gas configuration. And then the valence electron, well, the valence electron is the electrons that are beyond the nearest but lowest inert gas configuration. Okay? And also, when you're writing these electron configurations, say for sodium, you can write it as the neon configuration and then just show the valence electron, 3s1. All right, so as we go across that third period here, everything's very normal. 3s fills up first, then the 3p's fill up. All right, but now we get to the fourth period, from potassium to krypton. Now, fourth period, what happens here is that those first two electrons go into the s states. They do not go into the 3d states. They don't, because those s electrons are lower in energy. Those s states are lower in energy than the 3d states. And so these electron configurations are argon 4s1, argon 4s2. And then once we fill those 4s states, well, then we start filling the 3d states. Okay? So here's scandium, here's titanium, here's vanadium. Everything's normal, 3d1, 3d2, 3d3, and then we get to chromium. Right, da-da-da. We have an exception here, chromium. Chromium is not what you would expect. Chromium is 4s2, 3d4. Is not 4s2, 3d4. Chromium is 4s1, 3d5. There's really no way for you to know that a priori unless you do a very sophisticated calculation. But this is experimentally observed that this is the configuration. Why? Because it's lower in energy, in total energy, than this configuration. All right? It turns out that there's some extra stability in having a half-filled 4s shell and a half-filled 3d shell, subshell, compared to having a filled 4s shell and a less than half-filled 3d shell. Okay? This is an exception that you do have to know. Okay? Okay. But after chromium here, manganese behaves well, iron behaves well, cobalt okay, nickel okay, and now we get to copper, dun 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 dun, and we got a problem. It is not what you would expect. It is not 4s2, 3d9, and instead it's 4s1, 3d10. Okay? Again, this configuration is something you couldn't have predicted a priori. If you do a sophisticated calculation, you can see it. But this is also experimentally observed. We know this to be the configuration. This is not the configuration. All right? This is the lower energy configuration. Here's another exception that you have to know, copper. Right? Okay, and then after copper here to zinc, things follow a pattern again. The next electron then just fills up the 4s2, 3d10. Now at gallium, all of those are filled. We start filling up the 4p states. All right, and everything's fine until as we get to krypton. All right. So you got to know chromium and copper. Now, the fifth row here, starting with rubidium, strontium, ytterbium, zirconium, etc., all the way across here. Well, starting with rubidium, again, the electrons go into the 5s shell. They don't go into the 4d. And that's because with rubidium and strontium, 5s is actually lower than 4d. And it's only once you fill up the 5s states that you start filling up the 4d states right here. All right? Now, there are exceptions along this fifth row. And the two exceptions, molybdenum and silver, are the same kind of exceptions as chromium and copper. All right? You have to know the exceptions for silver and copper and molybdenum and chromium. All right? The same identical kind of exception as in the fourth row here. There are other exceptions along this fifth row. You don't have to know those. There's really no way a priori for you to know that. Again, it's an experimental observation. A sophisticated hard calculation will also show that. All right? Okay. And then once you're done with cadmium, well, then the 5Ps start filling, and everything's normal, and you get to the xenon inert gas configuration. Okay? Okay. Okay, now, how do you remember what the ordering is of these states, the energy ordering? Well, here's a mnemonic that maybe some of you have seen before. But start out, write 1s, then write 2s right below it, and then 2p to the side of it. And then write 3s, 3p, 3d. And then write 4s, 4p, 4d, 4f. And then write 5s, 5p, 5d, 5f. And 6s, 6p, 6d. And 7s, 7p. And now to get the energy ordering, we're going to draw diagonals. Well, first of all, the 1s is the lowest energy state. And then the next highest energy state is the 2s state. And then the next highest energy state is the 2p. So we're going to draw a diagonal. So the next state to fill is 2p. The next one is 3s. Now we're going to draw a diagonal. Again, the next one to fill is 3p. The next one to fill is 4s. Draw another diagonal. Next one to fill is 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5s, 6d, 7p, and that's all that's going to be important. All right, so that's one way to remember the relative energy orderings here. And you do have to be able to write this down on an exam, okay? Without, you'll have a periodic table, but it won't have the electron configurations on it, okay? Okay. Now, I want to tell you something that sometimes people find a little bit confusing. And that is the electron configuration of ions. What I'm about to say has no effect on what I just said about how to write the electron configuration for neutrals. Okay? This does not affect anything in your writing down the electron configuration for neutrals. This is for ions. Okay, but the point I want to make is that if you actually look at the energies of the individual 3D states and 4S states across that fourth row, this is what they look like. So for example, at potassium, that 4S state is lower in energy than the 3D state. That's why we put the electron in the 4S state when we wrote the neutral. And the same thing for calcium. That's why we put that electron into the 4S state and not the 3S state. But lo and behold, right here at scandium, Z equal 21, what happens is that the 3D state actually drops below in energy than the 4S state. These are the energies of the individual state now. Okay? And that continues all the way across the periodic table. However, that does not affect how you write the electron configuration of the neutrals. So for example, if you're writing the electron configuration for titanium, here it is. It's the argon core, 4s2, 3d2. Okay? And by the way, I don't care whether you write 3d2, 4s2, or 4s2, 3d2. Okay? You can write them in either order. All right. Now, you might say, well, why is this the electron configuration if at this value for Z is equal 22, titanium, the 3D state is lower than the 4s state? Why don't these 4s electrons just hop into the 3D states? Well, they don't do that. They don't do that because this electron configuration actually minimizes the electron repulsions. If these 4 electrons were in the 3D state, well, then the repulsive interactions would be greater because they're in the same state now. And therefore, the entire energy of the atom will be larger, all right? And it is the entire energy, the total energy of the atom, that's important when we look at the electron configurations. In this particular case, if we look at the individual D states and the 4s states, yeah, the D states are lower in energy. But what's important is when we sum up all of the energies of the interactions, what is lower? And what I'm saying to you is that when we do that, when we sum up all of the interaction energies, this still is the lower energy configuration, even though the 3D electrons at this value of Z are, those 3D states are lower in energy than the 4s states. Okay? So that's why we don't have this hopping over into the 3D states for the neutral. But now, here comes the ion configuration. If you have this configuration for the neutral, and now you ionize titanium to make titanium plus, the electron configuration is argon 3d2. That is, it's the 4s electrons that come off, that are plucked out, right? They're plucked out because they're the higher energy electrons now. Okay? So this is the electron configuration for titanium plus 2. So we're going to pull out those higher energy electrons, which are the 4s electrons. And again, this affects only the ion configuration. Same thing happens here on the 5th row. In the 5th row, starting here with rubidium and strontium, 5s is lower in energy than 4d. That's why that rubidium electron went in the 5s state. Same thing with the strontium electron went in the 5s state. But right here at ytterbium, the 4d state goes below in energy the 5s state. Again, that does not affect how you write the electron configuration of the neutral. So for example, silver, which is way out here, and which is one of those exceptions, okay? Silver, if you ionize it, if you pluck off an electron from silver, which electron is going to go? 5s. And so the silver plus 1 electron configuration is the krypton core 4d10. It's that 5s electron that's going to disappear. Okay? So this is important. Don't let it confuse you with the writing the electron configurations of the neutrals. All right? Okie dokie. See you Friday.